Hi class, in this lecture here we now want to talk about optimization problems, and this is just another application of differentiation, and these are really fun problems. And in this section all we're going to do is we're going to talk about, or we're going to learn how to solve applied minimum and maximum problems. So you got to think, how do we find max and mins, right? That's the first derivative, right? So it's going to involve the first derivative, and then you'll actually see I'm going to end up using the second derivative test to determine if it's an absolute max or if it's a min or a max, excuse me. Okay, so we're going to follow this procedure, all right, to solve these. And what I have here worked out for you is I have 6 examples that we're going to do. And you're going to notice they're all word problems. And they're fun. And I'll work through everyone's going to be different, you'll see. But even though every problem excuse me, is going to be different, the procedure that we follow to set them up is actually still all going to be the same. Okay, so here we go. So how we're going to solve these problems. All right, the first thing you're going to do is you're going to identify all given quantities and all quantities be determined. Sometimes not every problem, but sometimes it'll help to make a sketch. Then the most important thing is you need to write what's called a primary equation, okay, for the quantity to be maxed or min. And so this is the equation. This will make sense. This primary equation, so this equation we will use the calculus on. All right, because we want to max or min it, okay? So that's where we're going to look at the first derivative. Then what's going to happen, you're going to notice that generally these primary equations are going to involve 2 variables. Okay, so you're going to reduce the primary equation to having one single independent variable. Okay, this is going to involve some type of secondary equation. Okay, and what you're going to notice with the secondary equation, what we're going to do is we're going to plug this into the primary equation. All right, next you're going to determine the feasible domain of the primary equation. That is, determine the values for which the stated problem makes sense. Like you'll notice sometimes the problems will ask you for like length and width, so you can't have a negative number, things like that. And then you're going to determine the desired maximum and minimum values by all the calculus techniques that we've discussed, all right, in all the previous lectures. Okay, and so I'll start with some easy ones and I'll build to some harder ones here. So we'll start with this. Find 2 positive numbers such that their product, when you multiply them, you get 185. But when you sum them, you get a minimum. All right, so here's the thing. There's an infinite number of numbers, right, that when you multiply them, you get 185. Like 1 times 185, 2 times 185 over 2, 3 times 185 over 3. Like you can just see the pattern there, right? So out of all those infinite values, we need to find the value of the 2 numbers that sum, okay, is the minimum of all the possible values. All right. So look, let's start with this. We're looking for 2 numbers. So I'm going to start off by saying let's let x equal the first number. And let's let y be equal to the second number that we're looking for. Okay, so remember, looking back here, we need a primary equation and then a secondary equation. Okay, primary equation and a secondary equation. So the primary equation is the equation that you want to apply the calculus to. Okay, so you want to find the sum is the minimum. So the sum of these 2 numbers is the minimum. So that's the calculus part. So what I'm going to do is I'm going to just let this variable s equal the sum, and s is equal to x plus y. All right, but notice it's 2 variables, right? Okay, so the second part here, this piece of given information, their product has to be equal to 185. So x times y has to be equal to 185. Well, look at this. I can solve this and just for y. So y is equal to 185 divided by x. So I'm going to take this and substitute into our primary equation. So look, the sum is equal to x plus, and then y I'm replacing with 185 over x. All right, so now apply the calculus, right? So, if I want to minimize this, let me find the derivative, right? So the derivative of the sum with respect to x is equal to 1 minus 185 over x squared, right? Like I bring this up as x to the minus 1, and that's how I get this. So next you're going to do is you're going to set this equal to 0. So I'm going to move this over here, okay? So if it helps to see, s prime here, the derivative, is equal to 1 minus 185 over x squared. I'm going to set that equal to 0, right? Because I want to find the critical values. So I'm going to add this over. I get 185 over x squared is equal to 1. X squared is equal to 185. And now look, I said I needed two positive numbers. So x is equal to the square root of 185. So now here's the thing. You actually, this is what I'm really interested about this problem. You actually don't know if you found a max or min. So what you're going to do is you're going to use the second derivative test. To determine if you have a max min. So the second derivative of this, that's 0. You get 2. Bring this up as negative 2. Negative 2 times negative 185 is 370 over x cubed. And if you evaluate this for 185, like if you were to plug 185 into this, it's greater than 0. So what that means is you found a min. Okay, so x is equal to the square root of 185 is a min, which is perfect. Perfect. Okay, so what that means now, look, well, what are our two numbers now here? Okay, so just going back, x we found is the square root of 185. And what is y equal to? It's 185 over the square root of x. So it's 185 over the square root of 185. And you could rationalize the denominator if you wanted, right? Just get the square root of 185 times the square root of 185 divided by it would just be 185. So this is just the square root actually of 185. So hopefully not too bad. All right, let's do another one here. All right. Let's find the length and width of a rectangle that has a perimeter of 100 meters. Okay, so that's the perimeter is 100 meters of this rectangle. All right. And a maximum area. So you only have 100 meters of, let's say, fencing, right, for this rectangle. Okay. And what you want to do is you want to take that 100 meters and you want to maximize the area here. All right, so I'm looking for a length and width, right? So let's let x be equal to the length, and let's let y be equal to the width. All right, so this right here, I want to maximize the area of the rectangle. So this tells me this is the calculus part. Okay, so I have my primary equation. All right, I want to maximize the area. Okay, so that's area is equal to x times y, right? Well, what is the secondary equation, right? I gotta plug this in somehow. Well, I have this constraint variable, right? The secondary equation is the perimeter. All right? And that's, 2 times x plus 2 times y is equal to 100. Well, let me solve for y. Let me move the 2x over. Let me divide everything by 2. And look, I can take this in, and wherever I see y, I'm going to substitute this back in. So sub into primary equation. All right, so area is equal to x times 50 minus x. Area is equal to, just distributing here, right? 50x minus x squared. So if I take the derivative of the area function, area now with respect to x, I get 50 minus 2x. Well, look, you can move this over to here now. This find out where the critical values of this. All right, I'll just write it as a prime is equal to 50 minus 2x. Set that equal to 0. So you get 2x is equal to 50, or x is equal to 25. Well, again, second derivative test. All right, let's find a double prime. Well, if you take the second derivative, the derivative of this, you just get minus 2. And when you evaluate that for 25, you just get minus 2, which is less than 0, which means you do have a maximum. You found the maximum value. So look, we know x is equal to 25, and y is equal to, going even back here, it's just 50 minus 25, which gets me 25. So these right here, the length and width, that maximize that area here. Going back and circling this as well here. All right, so that was just two quick examples here. So what I'll do, just to break it up a little bit, I'll do the next 4 examples in a follow-up video here, just so this is just to break it up a little bit, just so you can see, take a little pause here. But the idea is to find that primary equation, okay, and then use the secondary equation to sub back in. All right, so I will continue with examples 3, 4, 5, and 6 in the next lecture.